We will start with the presentation on the development of silicon-based anode materials. The content consists of 4 sections. In introduction, we will discuss why lithium-ion battery is needed, the comparison of graphite and silicon as active material, and the problems of silicon. Looking at the graph on the left, Hubert predicted that oil production would decrease as the year 2020 approached. This supported the development of new technologies. Landsea temperature graph shows an average rise and a sharp rise in temperature after 2000. Also, the use of fossil fuels increased the amount of carbon dioxide emissions. By country, the figure is still high and overall it still has high emissions. For these reasons, it is also necessary to replace new technologies and fossil fuels. So we believe that the development of energy storage devices should be done. The structure of the lithium-ion battery consists of cathode, anode, and a separator with electrolytes located between them. Increasing energy density, increasing cycle life, and increasing capacity are important tasks for these lithium-ion batteries. Typically, graphite and silicon are used a lot as anode materials. First, graphite is currently used as a mainstream anode material for good cycle stability and low cost. The graphite capacity is 372 milliampere per gram, and high capacity is essential for devices and electric vehicles. On the other hand, silicon has a capacity of 4,200 milliampere per gram, which is 10 times higher than graphite. Also, silicon has high capacity in lithiation due to lithium movement, and with a relatively low discharge potential. There is a huge amount in the Earth's crust. There are some problems with using silicon. Lithium moved and combined with silicon. The unraveling process is referred to as lithiation dilithiation. Lithiation causes the volume of the silicon frame to expand. If you look at the picture on the right, you can see that silicon nanowires are centered around the lithium, creating a thick layer. Therefore, when silicon is fully lit up, the volume is tripled. This causes high internal stress on the silicon, resulting in geometric decomposition. Continuous volume changes and loss of electrical conductivity also occur. The formation of unstable SEI layers and repeated growth are also problematic. To solve these problems, we have studied new anode materials based on silicon and will introduce them to you. To measure only the capacity of the battery's anode material, the other parts are measured using a fixed half-cell structure. The silicon structure that we make is used as an active material and only this part changes. Mix the active materials, conductive agents, and binders to form slurry and apply them to copper foil to make electrodes. In this study, 3 silicon-based materials were manufactured as active materials. We will compare the performance of the half cell each made of materials what we made. The 3 are nanosilicon, porosilicon, and carbon-coated porosilicon. First, unprocessed nanosilicon was used as a comparison group for other materials. We found the best slurry composition ratio using nanosilicon. The second is porosilicon. Porosilicon was produced by oxidation reduction of magnesium silicide. I made a half cell with the slurry ratio that I found earlier. We want to make sure that a porous structure can solve the problem of volume expansion. The third produced porosilicon coated with carbon through the carbonization process of porosilicon. This will confirm whether the carbon cutting can solve the problem of volume expansion. According to the detailed experimental process of porosilicon, magnesium silicide was annealed, oxidized, and etched using hydrogen chloride. The final result will be porosilicon. The detailed experimental process of carbon-coated porosilicon uses CTAP and pre-manufactured porosilicon. The polymer was formed through resorcinol and formaldehyde, and carbon-coated structure was created through the process of carbonization. From now on, I will talk about the results of the experiment. The order is nanosilicon anode, porosilicon anode, and cycle stability. First is nanosilicon anode. We measured the capacity of anode materials based on silicon, and the radio of slurry is different. For the initial capacity, the 7 1.5 radio was 3951.36 milliampere per gram. The 7 to 1 radio was 3521.63 milliampere per gram. And the third was 3486.06 milliampere per gram. The radio reduction was 81.417%, 83.535%, and 81.52% for each radio. Therefore, the first radio was the most efficient, and the capacity reduction was the smallest. The bottom line was to determine the radio of slurry in this experiment, and nanosilicon without any process was used as an active material for anode. Nanosilicon showed a significant capacity reduction, and nanosilicon is a reference material that can be compared to other materials. Next, we will look at the SEM picture of our anode material. The picture above shows the images of magnesium silicide and nanosilicon before the process, and the lower part of the process was taken after the process. If you look at the surface zoomed in, you can see a fine pore in the surface of silicon. The following data are measured using the XRD equipment of the magnesium silicide material before the process and the etching process after the annealing process. The porous silicon was produced after an oxidation reduction reaction. XRD was measured to confirm the removal of impurities through the etching process and the formation of a large number of pores on the surface. And it was possible to confirm that the magnesium silicide substance became a pure silicon through the etching process after annealing and separate the magnesium silicide substance into silicon and magnesium oxide. Next is the data comparing the capacity of the pure silicon and silicon with carbon coating material. Comparing the difference in capacity in the second cycle, the porosilicon was found to be 1.445 milliampere per gram, and silicon with carbon coating is 149 milliampere per gram. The 20th cycle was 1.11 milliampere per gram and 118.7 milliampere per gram, respectively. And the reduction in capacity was 23.4% and 20.3%, indicating that silicon with carbon coating had a small reduction in capacity. Silicon with carbon coating can prevent the reduction of initial capacity through the carbon coating process. This is the final section, the conclusion. Initially, porosilicon and carbon-coated silicon were manufactured and used as electrodes to reduce large reductions in silicon capacity. The slurry radio of 7 1.5 was the most efficient. Since results are expected to vary depending on the radio of resinol and formaldehyde in carbon coating, The experiment is conducted in three proportions. Carbon cutting shows high capacity and capacity retention even at higher current. Porosilicon and carbon cutting were able to have higher capacity retention than nanosilicon anode by preventing the pulverization caused by silicon volume expansion. Thank you for your attention.